So we looked at what happens when we have like constant force. We work is force times distance, but real life is a little more complicated than that. Like it's very rarely that you'll like imagine yourself pushing an object. Are you actually able to maintain that constant uniform force throughout that whole like whatever distance you're going for? So what's actually happening is force is varying. So what ends up if you're able to plot your force for the distance. So for example, here's this is drawn some scenarios. So here's 3 different scenarios. So let's say first of all, I say we apply force, it gets bigger and bigger and bigger, and it tapers off and kind of becomes more constant. So that's an example of force. And let's just use the same example, similar to it. Okay, so more realistic ones are like the first 2. Apply force, and it's constantly changing. So for those that have done calculus already, what's actually happening, what you need to do is, because work is equal to force times distance, that's basically, if you look at the axes, that's just the area under the curve. So if you're able to, if you're able to integrate this area between 2 points, so some D1 and D2, that would give us the energy used from between those 2 distances. So this is a continuous line. And to accurately solve for, to accurately solve the area under the curve, calculus is required. However, many have not done calculus, and calculus not required for this course. So there's some other strategies that you can use to solve for it. So one is you can use approximations. So if you had data like this, we don't know how to explicitly solve for that, but what we can do is you can approximate using like rectangles. So this, for example, if I were to draw rectangles of equal length and solve for those rectangles, the area of those rectangles, it should average out to fairly close. There are different strategies. These are called Riemann sums. So the type of rectangle I drew on this one is I lined up the left point always with the curve. So theoretically, what would happen is that the area below will average out with the area above. In this case, we can clearly see it's going to be an underestimate because there's more area below. But you can do a what's called Riemann sum where you line up the left edge of the triangle, or you can do the right edge of the left edge of the rectangle, right edge of the rectangle, and a more accurate one. So what I mean by that is, for example, let's say we have another curve. So notice this one I lined up the left point of the rectangle. I could line up the right point of the rectangle like that. Right, so you can line up the right side of the rectangle. Or even better is we can do the midpoints. You find the midpoint and you draw a rectangle. So find a midpoint and draw a rectangle. Find a midpoint and draw a rectangle. So there's different strategies. So these are called, so you use discrete data. This is called a Riemann sum. And you do learn more about these in calculus as well, but you have the capabilities of solving things like this. What we would likely encounter in grade 12 though is simpler data. So if we have these shapes of trapezoids, triangles, rectangles, we can solve for those. So for example, I say, I can just solve for this shape right here. I can solve for this shape right here, and so on. We get some nice, easy geometric shapes which you can solve for. So constant force is just a horizontal line, and changing non-zero slope. Okay, so you can solve for the different geometric shapes that we know: triangles, trapezoids, rectangles, squares, etc.